Guys, welcome back to TechDose, and in this video we will see the maximum width ramp problem, which is from LeetCode number 962. We will be looking at three approaches. So the first approach will be greedy, and the second and the third approaches will be the optimal approach. And I would request you to watch the stock span problem and the online stock span problem after this. Let's now look at the problem statement. In this problem, a ramp in an integer array nums is a pair I comma j for which I is less than j and nums at I is less than equals to nums at j. The width of such a ramp is j minus I. Given an integer array nums, return the maximum width of a ramp in nums. If there is no ramp, then we need to return 0. Now we will look at some example, but before that let's look at the constraint here. They are mentioning it has 5 times 10 to the power 4 number of items. So with these many items, if you write an n square algorithm, then with the given value of n, you can imagine that it will be 25 times of 10 to the power of 8. And we know that if we want AC, that means accepted, then we need to do it within 10 to the power 8 operations for 1 second. Okay, so an n square algorithm will not work in this case. Anything better than n square should work. Now let's look at some example for better understanding. Now let's say that our given array is 608,215. Now in this case, a ramp is said to be a segment of the array where you are starting at index I and ending at index j, where I should always be less than j and a at I should be less than equals to a at j. So these two conditions must hold true. Therefore, I can try with all the starting positions and take it as I. So how many ramps can I form starting from 6? Now starting from 6, you can only form one ramp which will end up at 8 because 8 is the only value which is to the right of 6 and is greater than 6. There is no other value to the right of 6 which is greater than 6. So the ramp width here is index 2 minus index 0, so it will be 2. Okay, so this ramp width is 2. Now can I form a ramp starting at 0? Yes, you can form 0, 8, 0, 2, 0, 1 and 0, 5. So in this case, the max width is coming as 4 for all the ramps starting with 0, which is for 0, 5, right? 5 minus 1. Now, can we make ramp starting at 8? No, because there are no elements to the right of 8, which is greater than 8. Can we make ramp starting with 2? Yes, we can make 2, 5, and there is only one ramp. So the index 5 minus 3, which is 2, will be the width in this case. And can we make a ramp starting with 1? Yes, because there is at least one element 5 to the right of 1. So we can make the ramp. So 5 minus 4 is ramp width is 1, right? So out of all these ramp widths, whichever is the maximum one, 4 will be our answer. Okay, so this is the entire problem statement. I think this is simple to understand. Now according to the constraint, let's do some observations. In this case, if you are given an array and let's pick two elements x and y pointed by left and right pointers, and they are at index I and j, then they can make a ramp only when x is less than equals to y and also I should be to the left of j. That means I should be less than j. So we can think like the ordering of two variables here affect our answer, and the first variable is the position. That means I must always be to the left of j. That means x must always be to the left of y. And the second thing is the value, right? Not just the position but the value here. Okay, that is array at L, which is x, must be less than equals to y, right? So these two variables actually affect our ramp making, and if we can order them somehow, then it will be easier for us to solve. So let's look at an idea of ordering all the items. So the first technique is based on ordering, which is sorting the array by value. We needed ordering based on two variables, that is position as well as value. So we have ordered it based on value, so that whenever I see a lower index and compare it with a higher index, then I will always be sure that the index 4 item will always be greater than the index 1 item, because we are sorting in ascending order, let's say. Okay, if we have sorted it. So we are sorting it based on value. Now if you just sort it based on value, then you will get this kind of an array for the given input array. And this is not giving me the idea of what is the gap. Like let's say, if I have to ask you about what is the gap between this 2 and 5, then 5 is to the right of 2 in the sorted array. And you might feel that, okay, the gap will be 5 minus 2, the index 5 minus index 2. But if you look at the original array, 5 is actually to the left of 2, which is not correct. This is not forming a valid ramp, isn't it? Therefore, just ordering by value is not enough. You have to order it by value as well as preserve the corresponding indices. So sort not just by value but also save the corresponding indices. And if we make a pair of this entire array where the value comma index is preserved and we sort it by value, then we will see something like this, okay, where two zeros are present and the first zero is saying I am from index 3 and the second zero is saying I am from index 6. This 5 here is saying I am from index 1 and this 2 here is saying I am from index 4. So if I have to check if 2 and 5 form a valid ramp, then I know that 5 is greater and to the right, but then actually is it to the right based on the original index? No, 1 is smaller than 4, so actually 4 should be on the left of 2. So this will not form a valid ramp, okay. So I think you got the idea about what we will be doing with sorting. So first I will be sorting it based on value comma index. And once you have done this, then we will be initializing two variables. First variable is the maximum width because I want to maximize the ramp size. So I will be taking it a value 0 because 0 is the minimum possible length, and if we cannot form any valid ramp, then we have to return 0 anyway. And the minimum seen is what is the index that we have seen till now? What is the leftmost smallest value index? Because if I want to extend the ramp to as much as possible, then I will want to make it point to the smallest valued index, and I will want this right side to go to the largest valued index in a greedy way, okay. So let's look at an approach. I think it will be clear. We will be starting at index 1 because starting at 0 actually do not give any valid ramp. Okay, so when we start at index 1 or b any index, I can always be sure that all the values on the right side are greater than all the value on the left side. That means greater than equals to, I can say. So I do not need to check the value. I just need to check the gap. Okay, so we see this value minimum seen. So the minimum value which you have seen, the minimum index is 3. What is the current index? It is 6. So what will be the ramp gap? It will be 6 minus 3, which is 3. So already known maximum width is 0. So 3 is better. So let's overwrite this. We will go to the next value. This is 2. Definitely this is ascending order. So we need not check the value. So 2 will be greater definitely. So we need to just check the gap. 4 minus 3 is 1. This is 3. So no change. Again go to this 3. Check the gap. 7 minus 3 is 4. So a better gap is coming. Therefore we will be updating this, right? You check this one, 4. The index is 5. 5 minus 3 is 2. This is already known as 4. So no need to update. Now this 5. 1 minus 3 is actually minus 2. And this minus 2 is coming because 5 must be to the left of 0, right? Now if you look at the index 1, this index 1 is even smaller than this 3. So I will update this to index 1 because we want to greedily extend the length of the ramp. As I said, any item to the right will always be larger. Therefore we can change the minimum seen index, try to minimize it as much as we can, right? Because all the items to the right will definitely be greater than equals to current item. Let's go to 6. So 6's index is 2. 2 minus 1 is 1. So no update. Again to 7. 7's index is 0. 0 minus 1 is minus 1. So no update definitely. And we will update this to 0. And when we go further, we are going out of bounds, we will stop, and the maximum width answer is 4 in this case, right? So this is a order of n log n algorithm, and the space complexity is order of n because we are taking an extra array which will be containing the index comma value. Okay, let's now look at the code before going to the next approach. This is the sorting approach where we will just get the original array. I will be building a pair of integer where the first value will be the value and the second value will be the index in the pair. And after this I will be sorting it in non-decreasing order, and I will be initializing the max width to 0, and the minimum seen will be the first index which is stored in the pair after sorting. And after that it is just a simple iteration from index 1 till the last index, and if we see that the gap is more than what is already known, then I will just update the max width. And if I see that the index, that means the current item index, is less than the minimum index already known, then I will reduce this minimum index so that we can form an even larger ramp. So this is kind of a greedy approach, right? And at the end we will be returning the max width. So this is the entire sorting approach. Before looking at the next approach, let's look at an idea. So the next approach is based on the problem of finding the previous greater element. If you have already solved this, the next approach will be very easy for you. Otherwise you can just go and solve the stock span problem. In this approach, let's say we have an array where we are given 520301, and I ask you about what is the previous greater element for each of the item. Now in order to do that, we have to maintain strictly decreasing curve. What is this? So this is maintained by monotonically decreasing stack, right? How to maintain a monotonically decreasing stack? In such a stack, whenever you see an item, if the stack is empty, you just directly push it. But if you see another item, and if this item is smaller than the given item which is already on top of the stack, then you directly push it on the stack. When you see a smaller item, you directly push it on the stack. But when you see a larger item, then you have to keep popping the items unless the stack is empty, or you see that the top of the stack is actually larger than the current item, and then you push the item, right? So this is the idea of maintaining a strictly decreasing curve, right? Now, how to find the previous greater element using this idea? Now for the first element, there will be no previous greater element. So let's write -1, considering that all the values will be positive. So I will be storing these values into the stack. Now if I store this value, let's say 5, then if I go to the next item and I want to find what is the previous greater element, I can just see the top of the stack, compare. So 5 is the previous greater element in this case, and push 2. When I go to the next item, I can see the top of the stack, and 2 is the previous greater element. I can push 0. When I go to 3, then I can see that the top is less. So I can keep popping the item unless I see a larger item or the stack is empty. So if the stack is empty, that means there is no previous greater element, but you see there will be 5 left, and so 5 will become the previous greater element, 3 will come in, okay? And then 0 comes in, you will push 0 on top of it and say that 3 was already the top, and then when 1 comes in, you can remove this 0, and then you see that 3 is present, so 3 will be the previous greater element. You push 1 and you are done with the entire process. So this is how you find the previous greater element. But then if I change this question and ask you about what is the distance to your previous greater element, okay, not you don't just find me the previous greater element, but what is the distance? Like if I say once previous greater element is 3, then I should not output it as 3, but I should output 5 minus 3. That means the gap. So if you want the gap, then you want to store the index of 3, because just knowing 3 does not tell you about what is the index. If I give you some random person's name, you will not know his home address and you cannot reach that guy. But if I give you the address without giving you the name, you can reach to that address and get the name too, right? So based on that idea, I will modify the stack and solve it by using the index. Now if you start iteration from the first index, for this one I will be storing -1 as an answer and store the index of 0. Okay. Now when you reach to this 2, then what is the previous greater element? The previous greater element you have to check with the stack stop. So this is just the index, check the value. So 5 is actually greater than 2. So yes, 5 is the previous greater element. And what is the gap? That will be the current index minus this 0. So I can just write 0, that is the previous greater element, it has index 0, right? And I can push index 1 on top of it. This does not mean that I am not maintaining strictly decreasing curve. It is strictly decreasing, but instead of storing the value, I am storing the index. Now I can go to the next item, and again when I see this 0, then I can just compare with the top of the stack. Yes, 2 is larger, so the previous greater element is at index 1, and I can just push this index, which is 2. Again when 3 comes in, then I know that the top of the stack is 2, the value is 0, so which is less than 3, so I can just pop it off. Again once index value 2 is again less than 3, so I can just pop it off. 0 index value 5 is greater than this 3, so 5 will be the previous greater elements, it index 0 can be saved, and then this index 3 will be pushed, and likewise I will continue to process it. So by this I can exactly say what is the distance from this item, let's say 3, to its previous greater element by just subtracting this 0 from 3, isn't it? But let's say that I change the question and ask you about find the farthest previous greater element, right? What is that meaning of this? So let's say that I'm solving the farthest previous greater element for this 1, right? So if you think about the previous greater element according to this approach, it will give you 3. But if you had not taken this 3, then what would be your next previous greater element? It would be 2. If you had not taken this 2, then your next previous greater element would not be present. What this means is for all the decreasing curve, okay, wherever you are present, what is the previous greater elements options that you are finding? And if you want to extend the length, if you want to extend the gap, maximize the gap, then out of all the first options that you had got, I will be taking the leftmost first option, okay, in the previous greater element. So based on this, for 1 the answer should have been 2 and not 3 when I am talking about the farthest previous greater element. So this cannot be solved in just one parse. I will show you the 2 parse process how to do this. Let's see the first parse. In the first parse, I will be moving from left to right and I will keep pushing the items, that means the index, in the strictly decreasing curve. So let's push this up. So index 0 will come, then index 1 will also come because 2 is less than 5, and again index 2 will also come because 0 is less than 2. But when you talk about 3, 3 is not less than 0, 0 is not less than 0, 1 is not less than 0. So once I go from left to right, then we will be maintaining the strictly decreasing curve, only the leftmost strictly decreasing curve, not beyond that point. Because if you had seen 3 and if you started popping off this 0 and 2, then you will lose this 2 and 0. So you will not get the farthest previous greater element. So the farthest previous greater element will only be served when there are 2 curves, 2 decreasing curves, and you see 2 correct options for you. Like let's say your item here was X and you see that the previous greater element 2 options are there. So I should not select the nearest item, I should select the farthest item. Therefore, whenever I maintain the decreasing curve, then I should not overwrite it. If I see any higher value, I should not start popping off from the top of the stack. So this is the simple rule change. When you compare the normal previous greater element, the normal monotonic stack, with the farthest previous greater element problem, which is just a modified version of the monotonic stack, right? So I think this is kind of a tricky approach. You might not find it very intuitive. Yes. So we are done with first pass. Now, since we want to maximize the width, so the maximum width can happen ideally if I form it with the last index. If it is not possible to be formed with the last index, then with the second last index. If again it is not possible to be found with second largest, then with the third largest. So if you, for the same start point, let's say for 0, the ideal case would have been from index 2 I can form a ramp with index 5. That would be the most ideal case, right? So maintaining that, I will be taking a variable, let's say max width, and I will be assigning it a value, let's say 0. That means I don't know the max width yet. And I will do another parse which will go from right to left. Okay, and then I will be comparing this value. So let's say this is 1. The top of the stack, index value 2, has a value 0 which is less than equals to 1. So definitely this can be a valid ramp. And if this can be valid, compare the width 5 minus 2 is 3 and already known max width is 0. So let's update this to 3. Now I will pop the top of the stack because maybe the previous item would have been 0.5 and that would also be a candidate to be forming a ramp with 1. Like let's say it was 0.2, then 0.2 would have also formed a ramp with 1, right? So I will just pop it off and I will just stay here. Now the top of the stack is index 1, which is value 2. Now this is larger than 1, so we cannot form a valid ramp ending at 1. Now we will go to 0. Now 0 is also less than the top of the stack, which is 2. Again 3 is greater than this 2. That means we can have a valid ramp here and the ramp width will be 3 minus 1, 2. But already known width is 3, so no update will happen, right? Now I will keep popping off the item unless I see a larger value and keep updating the max width value. So you can see this 5. Can this 5 be the starting point of the ramp where 3 is the ending point? No, because 5 is having a larger value. So we are done with this 3. We come to 0 again. 0 cannot be endpoint, 2 cannot be endpoint, and we are done, right? So when we are done, the max width value is 3 and this is the answer. So I hope you understood the approach of finding the farthest previous greater element as well. Now based on that idea, if the values can be enumerated in the form of a curve, and let's say the orange value is index and the yellow one is depicting the value of the array, then if you maintain a strictly decreasing curve, then you will get 5, 3, 2, 0. If you are not overwriting, if you are not popping off from the stack, we are just pushing it when you go in the first parse from left to right. So first parse, you don't need to pop any item. Whenever you see a lower item, just push it on the top of the stack. So which items are you pushing? 5, 3, 2, 0. You see the indices 0, 1, 4, 5. Why did we do like this? Because we want to find the farthest previous greater element. So let's say for this 2, the previous greater element could have been 3, or there could have been some better options like why not 4 and why not this 3, right? So out of all these options, you will find that this 3 at index 1 would have been the best option, isn't it? So I will take that instead of any other option. So what I do is when I see a 2, I will have a maxed width of 0. So I will start parsing from right to left. I explained you why I am doing from right to left, because I want to have the largest possible ramp from any given starting point. So let's say if the starting point is this 0, which is the lowest value in the monotonically decreasing stack, the top of the stack will always be the lowest value. So if I'm starting at index 5, I want to find the largest ramp. So I will definitely be ideally want the last index to be checked first, right? If I can form directly with the last index, then there is no meaning checking with anyone in between, because if 0 and 2 can form a ramp, then why should we check with 8, 7, 6? Because they will always form ramps of smaller size. So I am interested in forming a ramp of larger size. So why should I do that, isn't it? So it is based on this idea. So if I check this 2 with the top of the stack, which is 0, then 0 is less than equals to 2. That is fine. So it can form a valid ramp. Now the gap is 9 minus 5, which is 4. So max width can be updated to 4, and I will pop this item off. Let's see the next option. The next option is 2. Again, 2 is less than equals to 2. So this is also a valid ramp. What is the gap? 9 minus 4, which is 5. So let's update max width to 5. I will also remove this. Okay, why I am continuously removing all this? I removed index 5 and then I removed index 4, because I don't care about these guys now making any ramp from any other items in the middle, because I have already made a ramp from index 4 to index 9. So there will be no larger ramp forming when I start from index 4 and stopping before the last index, isn't it? You think about it carefully, you will get it. Check this value 2 with value 3. Again, 3 is larger, so no need to do anything. We will go to the next value. 0 is again smaller. This 3 is equal, so yes, it is a valid ramp. And if you talk about the width, 7 minus 1, which is 6. So 6 is larger. Update this to 6. Pop it off. Now check it with 5. Now 5 compared with this 3, 5 is larger. So just move back. Again 4 compared with 5, 5 is larger. Then 0, then 2, then 4, then 8. Okay. So 8 is larger. Now the gap between 8 and 5 is 2 minus 0, which is 2, but 6 is larger, right? Compare this 3, 3 is smaller. Okay. Now you have ended. So we have done this 2 parsing, right? And therefore you can make out that the time complexity will be order of n, because we are doing linear one time from left to right or one time from right to left, and the space complexity will be order of n, because we are using a stack and all the items might be in the decreasing order, so the stack size will be order of n. If you want a cleaner dry run, then I will give you another dry run with a smaller example. I will do one dry run from left to right, and I will always keep pushing the index as soon as I keep on seeing the lower values, but as soon as I see a higher value, I will not do anything. 0 is again higher than this 0, because it has to be strictly decreasing. 1 is also not strictly decreasing, so this will be the stack when I go from left to right. Again, when I go from right to left, then I will check my max width. Okay, I have already defined it here. Max width equals to 0. Now you check it out. This 2 is the starting point. It is less than equals to ending point. So yes, this is a valid ramp. Width is 5 minus 2, 3. So update this to 3. Pop this off. This 2, can this be a starting point? No, because 1 is smaller. So just move to the previous item. 0 can be the endpoint? No. 3 can be the endpoint? Yes. So what is the gap? 3 minus 1, 2. But this is already 3, so no need to update it. Right. So you just pop this off, and now this is index 0. Can this 5 be the starting point and 3 be the endpoint? No. This is not in correct order. And that is why we will move to the previous item again. This is also not in correct order, and we are done. So the maximum width in this case is 3. So the time complexity is order of n, space complexity is also order of n. Let's now look at the code. In this code, we are given the nums array, and I have declared a stack. So I will be keeping the strictly decreasing curve without doing any pop operation, as I said, and I have already explained why I am doing this. Then we will be taking a max width, and I will be iterating for all the index from the rightmost index till the starting index. I don't think you need to take index 0, but I have just taken it. And then you need to check if a valid start point, that means if the top of the stack is actually a valid start point and the current index is a valid end point, then the gap of index can be updated by comparing it with the max width, right? and whatever you do, you have to pop the top of the stack so that a new top of the stack can be compared for a larger maximum width, right? Once you are done with the process, just return the max width value. So this is the stack approach. Now we will look at the third optimal approach, and before that, it is based on the idea, again the same similar idea, that if you are looking at two values L and R, okay, the L is pointing to index 0, R is pointing to index 4, then if I ask you about will this 4 be present in any of the ramps starting at 7? So if you start a ramp with 7, you can end up at 4, you can end up at 5, you can end up at 1, you can end up at 3. Then in all these cases, in all these kind of ramps, if they were valid, okay, that is what I'm assuming, if they were valid, then 4 would have been present in those ramps, right? So my question is, can you have any ramp? Like, let's say if this value was 30, then yes, I can have a ramp from 0 to 7, and so all the indices in between will be included, right? So this approach is based on the idea that if I'm seeing a right pointer, then I'm asking about, can I start from the left pointer? Can I start a valid ramp from the left pointer and end at any index greater than equals to R? At any index greater than equals to R. Is this possible? Now this question can be easily answered when you know if there is any item to the right of this right pointer, including this right pointer, which is having a value greater than equals to 7. Okay, greater than equals to 7. So let's say there is a value 50 and there is a value 30. Now, in order for you to compare if there is any value from this right pointer till the end which is greater than equals to 7, it is always in your best interest that you take the maximum value and just compare it with 7, right? You will not take any other value, second max or third max. The best option, the safest option is to take the maximum value. So I will take the maximum value and compare it with 7. And if the maximum value happens to be greater than equals to 7, then yes, it can be a valid ramp. Otherwise, it cannot be a valid ramp, isn't it? So the idea is to track the maximum value which is present to the right of right pointer, including the right pointer itself. Okay. So if I can just do that, I can do a pre-processing based on it. So let's say that I am given an array and I have found all the right max values. This means that what is the right max value at this 3? It will be the maximum value right from index 3 till the end of the array, and that value is 4, and that is why I have stored 4 here. Okay, so this is the pre-processing step. You can just iterate from right to left and keep a track of what is the maximum value that you have seen. The maximum seen will always be assigned to the last value, which is 1. And when you go here, you will be taking the max of 4, 1, 4. So you will write it 4. Again, when you reach here, max of 4, 0, 4. So you will write here 4. This is how you can keep iterating from right to left and keep a track of the max value. So this is the pre-processing step. Once you have done pre-processing, then I can take a left pointer at 0. A right pointer you can start at 0 or 1. Let's start at 1 because right pointer being at 0 does not make a valid ramp. In this case, a ramp can start at L and it can include R if it ends at R or at any index to the right of R. Okay. And in order to find this, the only condition should be the right max you are seeing at R must be greater than equals to this 7. Is it true? In this case, yes, it is 8. 8 is greater than equals to 7. This means what? This 8 means what? If you take the max value from index 1 till the end, you will see 8 as the maximum value, right? So even if 8 was not present here, even if it was 70, but you had 114 here, 114, then still the max value here would have been 114. Okay, and that means that even though your ramp can start at 70, cannot end at index 1, but still it will end at index 4, and so your right pointer will get included, isn't it? So in that scenario, in this case, in our current input, 8 will be included in a ramp which starts at L because the right max value is 8. And that is how I can say that at least my ramp size is going to be R minus L, at least. So I will be taking max width with 0 and I will be assigning a value 1. And I will just iterate this right pointer to the right. Okay. Now I see that the right pointer value 2 has actually a right max value of 4. That means from here on onwards, the max value is 4. That means I'm not going to see any larger value than 7, greater than equals to 7. I'm not going to see that. So the right pointer here, index 2, will never be included in a ramp which starts at 7, that means index 0. So why should I bother starting any ramp at index L? Let's do L++ and go to the next index. It is 8 now. Again, you check the right max value is 4, current left value is 8. So can any ramp start at 8? No, because you do not have any value greater than equals to it right from R to the end of the array. So this is also not valid. Let's move our L to this value. Now when L and R are same, I mean they will not form ramp because 2 minus 2 is 0. Okay, so I will move this right pointer to the right. Now at this point, can a ramp start at 2 and include this 0? Yes, because the right max value is 4, which is greater than equals to 2. This means that a ramp can start at 2 and can end at 4. So the right pointer will be included by default. Okay. So what will be the value here? 3 minus 2, 1. Already known value is 1, so no need to update this. Move the right pointer only. Now again, you can start a ramp at 2 and include this right pointer because R max value is greater than equals to 2. So the gap is 4 minus 2, 2. So let's update this to 2. Move to the right hand side. Now this 1. 1 is actually less than this 2. So no ramp will be present. Now do L++. Again, this is 0. So yes, a ramp will be present from 0 to 1. So what is the gap? 5 minus 3, 2. Okay, now we will move to the right and we are done. We are out of bounds. So the answer in this case will be 2. So this is the 2-pointer approach based on pre-processing and a greedy approach. So the time complexity is order of n, space complexity is also order of n. Let's now look at the code. In this code, we are given the nums array and we will be finding the right max value, but just iterating from the right to left. Okay, so this is where I'm calculating the right max values. Then I'll be assigning a max width and take the left and right pointer. You can take right equals to 1 as well. And then we will iterate until we go out of bound. And this is the invalid case where the left pointer is pointing to some item and the right pointer is pointing to some item. And this right cannot be included with the ramp starting at this L. So we will do L++. So we are doing that. And if we can form a valid ramp from L to R or anybody to the right of R where R gets included, then I will just update the max width. Okay, and we will go to the next item that means right ++. And at the end we will be returning the max width. So I hope you were able to understand all these 3 approaches. I know the video was lengthy, but it was important to explain it in detail. If you still have any doubt, then please comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of these programming videos. See you guys in the next video. Thank you.